Okay, so last time we saw that the resistance of a material is given by rho L by A. Do you remember this part? If yes, then type Y in the chat box. Type Y in the chat box. If you remember the formula for a resistance R is rho L divided by A, where rho is the resistivity, L is the length of the conductor, and A is the area of cross section. As we know, resistance R as a unit of volt per ampere, which is given by ohm. As the resistivity of the material changes with temperature, similarly resistance also changes with temperature. And for a conductor, the variation is approximately linear if the range is not too great. So if you don't consider a large range of the temperature, then just like resistivity, resistance also changes linearly, which is given by the same formula. Instead of rho, now we have a R. R is equal to R0 into 1 plus alpha T minus T0, where alpha is the temperature coefficient of the resistance or resistivity. And R0 is the resistance at T is equal to T0. Okay. Let's solve one problem. A copper transmission cable is 100 km long and 10 centimeter. One second. So we have a copper transmission cable which is 100 km long and 10 centimeter in diameter, carries a current of 125. What is the potential drop across the cable? Can anyone tell me? Hello. Can anyone tell me how to solve this problem? We have a copper wire which is 100 km long and 10 centimeter in diameter, and it carries a current of 125. What is the potential drop across the cable? Dishita, Suptika, Mehak, Ayush. Please type in the chat box how to do it. If you guys are not going to respond, then what's the point of solving the problem? We have R is equal to V by I, which is the ohms. Then we got R is equal to rho into L by A. Now rho for the copper, we can get it from the table, standard table. L is 100 kilometer. Should I use kilometer directly or should I convert to meter?
Convert it to meter.
Okay, good. So it will be how much? 10,000, 100,000 meters, and you got 10 centimeters, which is cross section area is pi, diameter is d square, no? So d square by 4. So it is pi by 4 into d, which is 10 centimeter means centi, means 10 raised to minus 2. So 10 into 10 raised to minus 2 square. That is your area A. Now once you get R from here, R for the copper you can get it from the table. L is 100,000 meters. Area is in meters square. Okay, and then from there you can get R. From R, because the current is known, we can find out the potential drop, which is V is equal to IR. That we can get. Now, how much electrical energy is dissipated as thermal energy per every hour? This we'll do later on. This anyway, I'm going to teach you today, this part. So that part we'll do later on. Second part, B part we'll do later. So let me write this as A. B part we'll do at the end of the lecture. Okay. So 2 this is not 2 millimeter. This is 2 meter. Just meter. 2 meter length of wire is made by welding the end of a 120 centimeter long silver wire. So we got a silver wire which is 120 centimeter, and we got a copper wire which is 80 centimeter. So this is silver and this is copper. Okay. Each wire of the is 0.6 millimeter diameter. So diameter D is 0.6 millimeter. The wire is at room temperature. So resistivities can be taken from a table. So there is a table given in the chapter which we can take it from there. The potential difference of 5 volt is maintained between the ends of the 2 meter composite wire. So potential across, say, let's call this is B and this is A. So VAB, potential across point A and B is 5 volt. What is the current through the copper section? What is the current through the silver section? So will the current through the copper section and silver section, means copper wire, copper part of the wire and silver part of the wire, will it be same or different? Hello.
It will be different.
So you are saying you got two wires which are like connected next to each other. So one is 120 centimeter long, one is another is 80 centimeter. So current flowing from say point A to B. Okay. The current will be different in different parts of the wire. The silver wire will have different current, copper wire will have different current. Hello.
Yes, sir.
Current will be different. Sure. Hello.
Yes, sir, because of different resistance.
But they are connected in series, na? So what should happen to the current? If they are
Yeah, it
connected
will
in
be
parallel, then current will be different.
same in
But
series.
same current will flow. Okay. So what is the current in the copper section? It is same as current in the silver section. There is no difference between. Okay, and how to find out that? We can find out. We can take R. Let me change the color of the pointer. R silver. Silver is AU, no?
Yes,
R
sir.
AU is rho AU into L by A. Okay, and then you have copper.
Sir,
R
it's AG.
AG, sorry, AG. RAG is equal to rho AG into L by A, and then your RCU copper, RCU is L by, so this is L1, L2. L1 is 120 centimeter and L2 is 80 centimeter. Okay, so by taking this one, you get a total resistance R is equal to RAG plus RCU. Okay, once you get a total resistance, you can find out the current. So you can get a current I is equal to V by R, V by total, VAB, which is 5 volt divided by the total resistance. Let me call this as RT. So you can get a current, and this current will flow. It will be same for both the part of it because they are in what is the magnitude of the electric field E in the copper? That you can find out. That it will be electric field will be same in both the copper wires. Both the copper wires will the electric field will be same. Sorry, both the wires will the electric field will be same.
No, sir.
Why? Why it will be different? Why it will be different? Why it will be different? See, what is the Ohm's law? It says J is equal to what is that? E by rho, rho into E. What is that? We have done the Ohm's law, no? What is Ohm's law? Where is our Ohm's law? Here it is. J is equal to E by rho. Okay. So let me go back here. J is equal to E by rho. Now what is J? J is nothing but I by A. Right? Now in both the sections of the wire, silver and copper, current is same. Cross-section area is same. So J will be also same. But because rho is different, electric field will be different. Isn't it? Hello.
Yes, sir.
Okay, J is same in both the cases. So E AG will be rho AG into J bar. Okay, and E copper is equal to rho copper into J. So we can now, can anyone just tell me which copper or silver, which one will have a higher electric? Silver is a better conductor than copper. Which one will have a higher electric?
Silver will have higher electric field.
See, rho for silver is less than the copper because silver is a better conductor than the copper. So rho for silver is less than the rho for copper. So now
Sir, rho is the reciprocal of
rho is the
resist.
resistivity. Rho is the resistivity. Hello.
Yeah, yes, I got it.
Rho is the resistivity. So which one will have a higher electric field? Silver part or copper part?
Copper part.
Copper part, because it has a resistivity is higher for the copper. So to create a same current, you need a more push. That means the electric field has to be higher for the same current. Now they are both are having the same current. Okay, to maintain the same current, because the resistivity of the copper is more than the resistivity of the silver, the electric field in the copper has to be higher than electric field in the silver. What is the potential difference between the ends of the silver section of the wire? That you can easily find out because you know the current I, and you can take R AG, and from there you can find out the voltage across copper wire or silver wire, any one of them. Okay, so E part also you can do. Okay, where is the magnitude of the E part in the silver? Copper and silver both are done. C and D both are done. Okay, so C and D both are done here. And E is very easy. E is what? What is the potential difference between the ends of the silver section? So V silver, which is V AG, is equal to current I into RAG. Right? Hello.
Yes, sir.
Now let's go to the next part. This is clear to everyone? Hello. Is it clear? Hello. Is it clear?
Yes, sir.
Okay. So let me go to the next part. Something called as electromotive force. So we'll go to the next part called as electromotive. Now we'll just start with the concept which is already discussed in the previous section, and from there we'll go to the next new part. Suppose we have a conductor. For a conductor to have a steady current, it has to be part of a complete circuit. Why a conductor has to be a part of complete circuit? Because if you establish an electric field E in an isolated conductor, that means just a piece of conductor, then current begins to flow with some density J. Okay, it results in accumulation of charge. So suppose you have a E in this direction. Okay, that creates J also in this direction. Okay, and that relation between E and J can be given by the Ohm's law. As soon as the current starts flowing in this isolated conductor, what will happen? There will be a positive charge accumulating because it is isolated. There is a negative charge which is getting accumulated. Okay, this accumulated charges creates their electric field. Now this accumulated charges, because there is a positive charge on the right hand side, negative charge on the left hand side, so they create their electric field. Okay, let me call this electric field as EI, induced electric field. So this will continue to happen till EI is equal to E bar. As soon as EI is equal to E bar, total electric field E total is basically made up of both the electric fields will become zero. As soon as electric field becomes zero, total electric field becomes zero, the current will stop. That means the J will become zero. This is clear. So basically, what will happen? You have applied electric field, charge got accumulated, and the current stopped. Okay. So we cannot have a steady current here. Okay, current will keep on decreasing because EI will be keep on increasing till it becomes equal to E. So current will keep on decreasing as soon as the current start flowing. Okay, then what to do? To maintain the steady current, charge should not accumulate but should go back to its starting. That means if you have a conductor and you want to maintain a steady current, then you should not allow the accumulation of charge. So what should happen? Once the charge reaches the one end, it should go back to its starting point. For this purpose, we need a complete circuit because the charge has to go back to its original position. That means we need to have a complete circuit in our hand. Now we know from the electrostatics that if charge goes around a complete circuit, that means it starts from a point, goes around in some place and comes back to its original position, then change in its potential energy should be zero. That means change in the potential energy of a charge, which who has a starting point and end point is same, will be zero. So it might change its potential energy in between, but again it will gain the potential energy, and when it comes back to its original position, the potential energy as it is. As motion of the charge through a conductor decreases the potential energy. So we know that if charge is flowing through a conductor, it's basically flowing in the influence of the electric field. If it is flowing in the influence of the electric field, what should happen to the charge? Its potential energy should go down. Then if this is a part of a complete circuit, then there must be a part of the circuit that increases the potential. So if I'll just show you, like let's consider a kind of a complete circuit. So we got a piece of conductor, okay, a electric field is applied, a positive charge is moving towards right, and there is one more box here, okay, and basically current is flowing from left to right. So positive charges in the conductor itself are moving from left to right. Now, as these charges move from one end to another, what happens to their potential energy? The potential energy is given by V. V is the potential energy per particle. It goes down, so potential energy goes down. So it reaches this end. Okay. Now let's consider that this part of the wire, which is shown by a line, is contributing nothing. Okay. The wire itself is a conductor, but let's assume that the wire has no effect on anything. Now, if charge goes from the starting point, say point A, goes around the circuit and comes back to point A, what should be the total change in the potential? Hello? Or potential energy? Hello?
0.
0. That means if it is going from point A to B, its potential is decreasing. Somewhere its potential should again reach back to its original position, isn't it? Hello?
Yes, sir.
So I have just drawn a box here, which is right now unknown to us. Now, what is the job of this box? Job of this box is increase the potential energy of the charge. So what this box is doing? Box is simply increasing the potential energy back to its original position. Okay. So charge started from A to B in under the influence of the electric field. Its potential energy went down. Okay. And in the wire has nothing to contribute, and there is a box which is right now unknown to us. In that case, what happens is potential energy increases. Now, can anyone tell me when the potential energy of the charge will increase? In what case the potential energy of the charge will increase? The way that if charge is moving in the direction of the electric field, its potential energy decreases. So in what case potential energy of the charge will increase?
When it will move in opposite direction.
Yeah, right. So this box has an electric field in the right to left. Okay. But what is happening to the charge? Charge is moving from left to right. Because charge is moving from left to right, opposite to the electric field, its energy will increase. So by the time it comes out of the box, it has regained its energy. Okay, electrostatic energy. Now it will go from here, come back to a point at the same level. So you can see the potential, which is a potential energy per particle, is same as the starting point. Okay, so box is a kind of object where the charge moves opposite to the electric field. We'll see how it happens, and in that process, it's gain its energy. Okay. Okay, now let's look at this box. Now, other part of the circuit we know already, but box is something which is new and which is different. That charges are moving opposite to the electric. Okay, so let's look at the box in more. So we got a box here. Okay, now this box has some material, something which applies a force called Fn. Okay, there is a force called Fn. Now this is a non-electrostatic force. What is a non-electrostatic force? Any force which is not related to the electric field. Okay, hello. Any force that is not related to the electric field is called as non-electrostatic force, like gravitational force, then chemical force, chemical potential force, force due to chemical potential, or any other type of force which is not connected to the charge of the particles is basically non-electrostatic. Okay, so there is a non-electrostatic force and in this box, and what this non-electrostatic force does is that it pushes the positive charges towards right and pushes the negative charges towards left. Is it clear?
Yes,
Fn
sir.
is a non-electrostatic. And you know what kind of instrument would do this job? Our normal uh, solid state battery, which is there in our mobile phone, our laptops, all the devices which operate on batteries. Basically, batteries are what? Basically, they have a chemicals which react with each other, and they create a force on the particles to move around, which is of not a electrostatic force. So that chemical force due to this chemical reaction is type of non-electrostatic. Now what they are doing, they are separating the charges, positive charges on one side, negative charges on the other. Now what this force will do, this force will create this type of charge distribution. So it will have positive charges on one side, negative charges on the other side. This force will continue keep on separating charges. So at one point what will happen, because there are positive charges on the left and right hand side and negative charges on the left hand side, a electric field will be created which is towards left, but Fn is a force towards right because it is pushing the positive charges towards right. So now any positive charge in between, we have two kind of forces, a force due to electric field towards left and force due to non-electrostatic force towards right. Now this will continue till both the forces become equal and opposite. That means if the charge has a magnitude q, then a point will come when electric field will be q into electric field will be equal to F. That time the process will stop. So you got the end of the process will be like you got positive charges on one side and negative charges on one side. Okay. Now just imagine that this object is a part of a complete circuit. Now what happens in that? A positive charge enters from one side, okay, and another positive charge goes out from the other side. Now what this positive charge will do, which is entering from the left side, hello, what this positive charge will do, which is entering from the left side,
It will be attracted fastly.
no, it will cancel out this negative charge. There are negative charges, so what it will do, there is a negative charge, there is a positive charge entering from the left side, it will cancel out the negative charge. So your process will become like this. One positive charge is gone from the right hand side. One positive charge which is entering from the left hand side has cancelled out one negative charge. So you got this. Now what happens, because the number of charges are less, QE becomes less than Fn. Fn is constant force due to the say some chemical reaction something. So Fn is greater than now QE. Now what Fn will do? Hello. What Fn will do? Again it will start
Push the charge.
separating, and it will start separating charges, and then again it will reach to the previous case starting. This is clear? Hello.
Yes, sir.
Now what has happened in the whole process, that a positive charge has entered from the left hand side and a positive charge has left from the right hand side. So it looks like you got a positive charge entering from the left side and positive charge going up from the right hand side. The box has not changed at all because what the box has reached its initial state again. So it's like charge entered from the left side and it went from the outside from the right hand side. Is it clear? Hello. Is it
Yes, sir.
clear? Yeah. But in the process, what has happened? The positive charge which was entering from the left side was having a electrostatic energy which was less, but the charge which was coming from the outside from the right hand side, it has a electrostatic energy higher. Hello.
Yes, sir.
So it looks like the charge entered from one side of the box. As soon as it came from the other side of the box, it got higher electrostatic energy because it passed through a electric field which was in opposite direction. So electric field of this box was towards left. Charge came from the left hand side and left from the right hand side. So it was moving against the electric field, and that was possible because of Fn, because Fn is a force which pushes the charges, positive charges towards right. So Fn has done the work on this positive charge, and positive charge has now gained the energy, or now it has a higher electrostatic energy. Is it clear?
Yes, sir. Clear.
So that's why when the charge passes through this box, its electrostatic energy will go higher. Now, what is this box? This box is basically, we see this type of boxes every day. So examples of this box is basically solar panels. Okay. Then we got a chemical cells, chemicals, batteries, then generators. Okay. In all these cases, your Fn will be, the source of Fn will be different. Like you have a solar panel. In the solar panel, what is the source of Fn? Is the chemical force, chemical potential force on the positive charges due to the photochemically, for electrically light chemical reaction which is induced due to the light. In chemical batteries, it is purely a chemical force, which is basically separating the species, positive charges and negative charges. In generators, it is a magnetic field that forces the charges to move around from one place to another. Is it clear?
Yes, sir.
Okay. I can give you one simple example. Let's say we got a magnetic field, okay, which is okay, coming out from the screen. And suppose we keep a rod like this. Now, suppose we move a rod towards left, sorry, right. What will happen to the charges? See, there will be positive charges, negative charges on the rod, right? Say it's a good conductor rod, so it got positive charges, negative charges. As soon as the rod starts moving towards right, all charges will feel a force to the magnetic field. Now it is really V cross B, B cross B. So when the rod say goes here and it is in the motion, positive charges will be on the lower end, negative charges will be on the upper. Hello.
Yes, sir.
Now the electric field due to this positive and negative charges is upward, but the magnetic force is downward. So in this particular case, Fn is nothing but the magnetic force. Okay, magnetostatic force, which is acting on the charges. Similarly, in the chemical batteries, it's a force due to the chemical potential. Now, what is EMF? EMF is a work done by a non-electrostatic force to move a unit charge from a lower potential, which is the left hand side, to the higher potential, which is the right hand side. Is called as EMF. It is called as electromotive force. But it is not a force, it is a work done per unit charge to go from a lower potential to higher. Okay, let's consider a left hand side as point B and right hand side as point A. Work done to move a charge from left to right is Q into VAB, which is let's say the potential bit at these two ends are VAB. So work done is QVAB. And why there is a potential? Because there are positive charges on the right hand side and there are negative charges on the left hand side. That's why VAB will be there because of the charge distribution. And the charge which is moving from left to right has to do work against that. And the work is provided by Fn. The total work done is Q, which is the amount of charge into VAB. So EMF, which is a work done per unit charge, is nothing but W by Q, which is EMF curly E is equal to VAB. This is clear?
Yes, sir.
Okay. So when you have a battery of 1.2 volts, normal torch batteries, which we have normally we use at normal at home, which is 1.2 volts, what does it mean? It simply means that when the charge moves goes from the negative terminal of the battery to the positive terminal of the battery, from the inside of the battery, the work done by the chemical reaction is basically 1.2 volt. Is it clear? Per charge.
Yes, yes, sir. Clear.
Anyone is having a doubt about this? Now this is a source. This box is nothing but a source of energy. Okay, which is basically push the charges against the electric field. Now I can give you a simple example in terms of a chemical thing. Let's say, sorry, in terms of some mechanical. Let's say we got a fountain. The water is going up and falling down. Okay. Now to maintain this fountain, the flow of the water, okay, what we have to do is that when water reaches the bottom, we have to push this water up by a mechanical motor, right, or pump. So water is basically pushed against the gravity up to this point. Then it will fall. It's automatic. So it is same like our electric complete circuit. A motor is like a battery or the source, and what you see here is like a current flowing through the rest of the circuit. Is it clear? So water can fall under the gravity, just like a charge will move in the electric field. But when it reaches the bottom, the potential energy has decreased, right? So you have to again give the push upwards so that potential energy will increase. So more, there has to be an instrument called as pump, which will do a force which is non-gravitational force and push the water upward again, giving it some higher potential energy. And then again water will fall down because of the gravitational force. Again the pump will push the same water up. What in our circuit, same thing happens. The charges move through the wire, external wire, because of the electric field. They go down, they have a less potential energy. Now we got a pump, which is nothing but a battery, solar panels, or your generators, mechanical generators, all those things. So they'll push the particles again to the air. This is clear? Hello.
Yes, sir.
Okay. So we'll stop here. Hmm? Next lecture, we'll do one more part and then we'll solve the problems, and next lecture will be mostly over with this chapter. And then we'll go to the next chapter. I'll give you the attendance link.